Welcome to the webinar about the Alpine Bridge solution. Today we will cover the topic about code-based design and checks. We will continue in our 160 meters long railway bridge example where we modified the number of tendons to balance more of permanent loads. At first, we will talk about additional definitions in cross-section and structural units. Then we'll continue with combination tables, complementing construction sequence, and end with the plot of the results. Let's start with the definition of property sets in cross-section. For the cross-section of the main girder, we kick it off with the definition of stress points at the vertices of the outline. This definition is needed for a more detailed calculation of stresses and their outputs in stress-related tasks. We set up a few reinforcement sets for longitudinal reinforcement layers by assigning a corresponding property set to the boundaries. Each reinforcement set can be named, assigned to a structural unit, boundary and material. To finalize the input, we enter the diameter of bars and tick the boxes if we want the reinforcement sets to be effective in shear and torsion calculations. If needed, there is always a possibility to define user input of reinforcement area, including variation by tables or formulas. This user-defined area is then considered in calculations. A modification by shifting the geometrical position of first and last bar can be done by position options. A very similar approach is applied to the definition of shear reinforcement representing stirrups. We input the boundaries, materials, and diameters. After the specification of a number of legs, or sometimes called branches, and user-defined spacing, we are all set up for shear calculations. In our example, we assume a total of 6 branches in stirrups from shear and torsion definitions of stirrups. In torsion reinforcement set, we will show a boundary assigning approach to the definition of geometry and set it as effective also in shear. The exposure classes are needed for proper design and checks in serviceability limit state. Let's see how to define them in our cross-section. We assign structural unit and boundary on which edges the zone will be defined. In our first zone, we apply the classes for carbonation, chlorides, and freeze or thaw attack to the whole boundary. As could have been seen in the scheme, we need to define different exposure classes at a part of the boundary between points 10 and 11. So we use a different definition only on a part of the boundary for the zone number 2. Let's go through the same process once again, this time for a pure cross-section. At first, we assign a longitudinal reinforcement set for the left part of the section, and then subsequently for the prepared boundary on the right side as well. All bars of diameter of 20 mm will be distributed automatically on this curved path, and we will set them as effective in shear and torsion. Only one stirrup effective in both shear and torsion is expected, and this time we use an automatic offset calculation that can be used on solid sections and sections with only one opening, such as one cell hollow box girders. An additional attribute of buckling lengths needs to be defined if we want to consider second-order effects in period sections. By clicking on the structural unit number, we can make an input of lengths in both directions. As could be seen in previous webinars, we can define the superpositions of load cases, and we will use them today in our combination tables. We create a new combination table number 1 and start the definition of our first combination C1. The type of the combination is ULS and we will include self-weight, superimposed deadloads, pre-stressing, creep and shrinkage, and all live and traffic loads presented in the final stage of the bridge. The definitions of combination C2, C3 and C4 are done in a very similar way for all SLS types of combinations. We apply correct factors by the code for favorable and unfavorable effects. The tables enable us to fill the factors very quickly by a keyboard or by copying the entire rows if needed. As you can see, the table combines both gamma and psi factors from the code for ULS and also SLS combinations. We will also prepare the ULS and SLS combinations for intermediate stages, as some of live and traffic loads do not exist at that time and would not be considered properly. To also show more options, let's assume 6.10a and b prescriptions from Eurocode will be used for ULS types. We will also put together combination C5 and C6 into a ULS group of combinations by ticking column number 1. After all these definitions, we can actually start defining the tasks in the construction sequence. Stage number 4 is a stage when the second span is activated and tension in tendons is applied. We will define linear stress calculation at first, as it might help us to quickly see if our design of tendons is sufficient. Linear stress calculation can be run on any type of combination type, so we select characteristic combination C7. The results in design and check tasks always needs to be stored under a specific result name. To finish the definition of this task, we need to define the assembly, in this case the whole second span length. The second task in stage 4 will be code design task, which produces the determination of required reinforcement in section for all necessary limit states. We select corresponding ULS group and SLS combinations from filter lists that will be assessed in 46 days and save the results under a result name. Again, an assembly is defined to finish the task. To see if user-defined or designed reinforcement area holds up against specific code limits in ultimate limit state, we can use ULS check task. ULS group is selected to cover all ULS combinations at given time of 46 days. The check can include the calculations for flexure, shear, torsion and their interaction with an input of theta angle for variable truss models. We will include result name and activate an assembly at midspan. To complement this, we can use SLS check task to see the results for serviceability limit states such as stress limitation and crack width, including decompression conditions for tendons. To cover all these checks, the code requires to select all 3 types of combinations or groups for pre-stressed concrete members. UlpamBridge will automatically assign them to corresponding calculation and formulas. To print out the results in a Word document, we can use check report task at this stage. The results for ULS and SLS check tasks are produced for a given result name and assembly. We can define a new construction stage where we will evaluate the code-based design and check tasks for the final structural system at the time of 100 years. We can use the same tasks as seen in phase 4 with the usage of combinations with all live loads. The code design task will use the same result name as the same task in phase 4 to cover the design situations most unfavorable from both stages. We will define an assembly in the midspan of the second span at a distance of d from the face of the pier and at the bottom of the pier number 2. difference between the usage of different or same result name can be seen on following example. Let's assume 3 construction stages with different results of necessary reinforcement area. If we save the results under the different result name, we can print out each of the results. If we use the same result name, the highest reinforcement area is printed out. The same principle can be applied for the checks with utilization as a decisive factor. We will repeat the process with the definitions of ultimate limit state and serviceability limit state checks for midspan section, the section at pier face, and at the bottom of the pier. Day specified in tasks is the leading component to determine the age of the element and cross-section or tendon state at checking time. It is also important for evaluation of creep, shrinkage and pre-stressing losses contained in the combinations. We will also once again repeat the definitions of report tasks for linear stress calculations, ULS and SLS tasks, and code-based design. As the assemblies are very often the same, we can save time by modification of TCL file with multiple reuse of already defined assemblies. The reports can be also produced on demand in 3D model by right mouse click button and selection of required report snippet at specific stationing. By clicking on Recalculation button, we run all geometry calculations, structural analysis, evaluations of superpositions and combination rows or groups. At the end, the complete nonlinear reinforcement design and checks are performed. Let's proceed to the overview of the results. The first option is to plot the results as a 3D diagram for a given result name. We can select a specific check like flexure or stress limitation and plot the corresponding values. When plotting the results of linear stress calculations, we can either plot the minimum or maximum stress for the enveloped results on the whole member, or we can see the results in specific stress point defined on the cross-section. The next option is show the results in the form of tables. By selection of specific results, we can either have a look at them or export them in a form of Excel spreadsheet. For a flexure check, there is also one more possibility to plot the results in form of 3D interaction diagram, where we can see a vector of bending moments and also the intersection with the interaction surface. Let's have a look at the produced snippet for flexure at the midspan, for shear in its most unfavorable stationing, where we can see the shear resisting part of this section and all detailed formulas given by the code. We can have a look at pier section for second order effects. These effects include geometrical imperfections and also second order effects calculated by the method of nominal curvature. These magnified moments are then assessed in the same way as for flexure. The design area of reinforcement per reinforcement set can be plotted in a design report. Let's show the last one for SLS calculations of crack width at the midspan. By showing this, we finished today's webinar. Come and join us in our next webinars for Alpine Bridge.